Swayam Prabha. Digital India. Educated India.
Hello everybody. Today we will discuss about one of the mostly used fusion welding process, that is a laser micro welding process. So already you have defined that the domain of the micro welding process in terms of the geometric size and shape of the fusion zone and heat affected zone. So in this case, at least one of the dimension of the part is less than 100 micrometer. Probably we can consider that under the category of micro welding process, and here the source of the heat from the laser. So we know that there is a unique advantage of laser welding process. The one thing is that it is a non-contact nature and high intensity of laser is focused into a very small area. So it is possible to define that laser micro welding process, which is in terms of the power density. So normally the laser welding process, the power density means the power per unit area which is focused on the surface of a substrate material, that is very high as compared to the other arc welding processes. So this is one advantage yes in laser welding process. At the same time, since it is non-contact nature and both metallic and non-metallic substrates can be processed using laser as a heat source. So the general configuration of the laser welding process, or in specific laser micro welding process, is similar to that laser welding processes. Only thing is that the dimension of the over which it is focused is less, and the mode of the laser may be in both continuous as well as pulse mode, can be used in case of laser micro welding process. So one of the typical laser micro welding process that is the laser transmission welding. Here the combination of the transparent material and the absorbing material can be placed in the different way, so that laser energy will be absorbed on the absorbent. So we will look into that further on the laser transmission welding, but before doing that we will try to focus on the other aspects of the laser welding process. If we see that physical aspects of the laser welding process, already we know or we have some idea about the laser welding process, that there is a two modes. One is the conduction mode, another is the keyhole mode. So in conduction mode, if we see that when the laser is focused on the surface, then it don't produce the much penetration within the oil pool, and there may not be any vaporization of the material. So probably it can be related in terms of the power density of the laser, which laser we are using, and we measure the power density when the laser is interacted on the surface of the substrate material. So first one is the conduction mode laser welding process. So in this case, the shape of the oil pool is little bit shallow type, not much penetration. But on the other side, we can define the keyhole mode laser welding process. But before that, we may look into the what are the typical aspects of conduction mode laser welding process. First is that power density is less than 10 to the power 6 watt per centimeter square. Normally we can consider that it is a conduction mode laser welding process, and the laser power is transmitted usually through conduction to the surrounding, and the penetration or depth of penetration or shape is mainly controlled by the heat conduction only. So, this conduction mode laser welding is we found out the typical applications, but mostly if we try to do that high depth of penetration, probably in this case the keyhole mode laser welding is more suitable. Now, if you see the right hand side figure, that laser is penetrated into the substrate material and it produces the high depth of penetration. So, this type of welding is generally considered as the keyhole mode laser welding process. So, what is the typical characteristics of this keyhole mode laser welding process? First is, in terms of the power density, we can define that keyhole mode laser welding process. So, in this case the power density is normally 10 to the power 6 watt per centimeter square. But apart from that, how actually how the keyhole can forms in keyhole mode laser welding process. So, since power density is very high, it try to vaporize the material, since the maximum temperature within the domain of the substrate material, it cross the vaporization temperature of that specific material. So, it forms a typical shape and over which a vapor domain exists within that substrate material, and that molten metal start vaporize, and basically it creates a blind hole, that is called the keyhole, and that within the keyhole the existence of the keyhole or it reaches with some steady state situation when it forms a vapor domain, and that vapor pressure actually keeps on live that formation of the keyhole. But sometimes we confused that if there is a formation of the keyhole, then what may be the why we cannot see after the taking the sample that keyhole size. So, if we see that these two figures, here it is very clearly defined that the fusion zone, and I think these materials are the stainless steel. So, and it is a laser welded material, and we have taken on the sample of laser welded sample, and then after polishing and etching we find out there is a fusion zone. We can identify the fusion zone, but we cannot identify the keyhole zone in this case, because keyhole forms during the welding process. So, once that switch of the laser source, then that space is filled by the molten metal, and after solidification we cannot see the size of the keyhole, but it is possible to theoretically calculate the keyhole size. So, that yellow line probably indicates the theoretical calculation of the keyhole during the welding process, and there exist several mathematical model to estimate the size of the keyhole. And other figure also you see is also stainless steel material, and this is the weld shape, and if we observe typically the shape of the weld pool, that indicates that there must be some formation of the keyhole in this case. Also, we can identify that if the power density in this case is much more above 10 to the power 6 watt per centimeter square. So, based on that also we can say this is the keyhole mode laser welding process. But one advantage of this keyhole mode laser welding process, because that due to the multiple reflection of the beam within that small cavity, that cavity means that size of the keyhole, that actually increases the absorption of the laser energy during the process. So, when there is a requirement of the high depth of penetration, probably the keyhole mode laser welding is more preferred as compared to the conduction mode welding process. But in terms of the micro welding process sense, that conduction mode is normally used for the micro welding process, because micro welding process we handle very thin sheet, maybe less than 500 micrometer or around 100 micrometer. So, in that case probably there is no requirement of the keyhole mode laser welding process. Now, further what are the different types of laser micro welding process? first we see that laser transmission welding. Now, we will try to explain the what is the laser transmission welding. From the figure it is very clear that laser beam is focused on the substrate material and over this transparent polymer is there, and the bottom side their absorbing polymer is there. So, laser is used in such a way that wavelength of this laser is chosen such that it can transparent to the upper side the polymer, but it's that within that wavelength it should be absorbed by the bottom side polymer, so that the heat will be released on the at the interface between the two substrate material. So, this is the typical mechanism of the laser microwelding process, laser transmission welding process. But in this case, if we try to join two transparent polymer material using the laser transmission welding process. So, in this case, if the laser beam or laser light is transparent for the both the material, then it is necessary to put one very thin absorbing layer between the interface, so that that layer will absorb the laser energy and finally it will melt the substrate material, and then we can form the welding process. At the same time, the laser transmission welding is possible to join between one polymer to another metallic material. So, first polymer, the first layer of the polymer, it is transparent to the laser, and the second we choose the metal in such a way that the second metal will try to absorb the laser energy, and there is a interface melting between these two substrate materials, and then we can form the weld between these two metals. So, this is the typical mechanism of laser transmission welding, and mostly several micro welding application we can find out this type of welding process. But there is another type of welding process based on the pulse duration, that is called ultra short pulse laser welding process. So, actually ultra short pulse laser is generally used for the material ablation, or maybe we can say the metal removal processes, but this laser can be used for the welding purposes. But before that we need to know that what are the typical characteristics of this short pulse laser, ultra short pulse laser. Normally for ultra short pulse laser we use the femtosecond pulse laser, femtoseconds or picoseconds pulse laser. So, femtosecond pulse laser, the duration of the pulse is around 10 to the power minus 15 seconds. So, within such small duration, if the laser energy is transmitted to the substrate materials, but the substrate materials specifically if we consider the metallic materials, for example, it is a metallic metal like gold. So, in that case within the such duration that there is a finite time is required to transmit the energy to the surrounding area. So, that finite time for any specific metal is even higher than that of the duration of the laser pulse. So, in specific to ultra short pulse laser welding. So, that pulse duration and the finite time of the heat transfer or maybe energy transfer within the metal is, these two are comparable. Then there is a effect of the delay, that means there is some delay in transmitting the heat flux needs to consider. That means this can be characterized by the some relaxation times. So, relaxation times in terms of the development of the temperature gradient within the substrate material, or relaxation time in terms of the heat flux applied to the substrate material, or maybe after applying the substrate material, what is the development of the that means development of the specific heat flux within the substrate material, that can also be delayed. And these two types of relaxation probably we need to consider in case of ultra short pulse laser, and it is not required in case of when the large or medium pulse laser processing or maybe medium or laser pulse welding processes. But theoretical aspect we will look into for ultra short pulse laser is very much different from the normal or medium or long pulse laser. Long pulse laser means we understand that it's a nanosecond and microsecond and millisecond. In that pulse duration, probably the energy, when the application of the energy from the laser is instantaneously transmitted to the substrate material. So, there may not be any lag phenomena. So, normally this ultra short pulse laser welding we analyze using the non-Fourier heat conduction or maybe two temperature models, assuming that there is a phonon and electron scattering or coupling between the phonon electron or scattering between the phonon and phonon. Based on that principles, we can estimate the different relaxation times when some substrate material is interacted with some ultra short pulse laser. That means any femtosecond pulse laser. Now, in that respect, we can explain that application of the pulse laser, if you see that in medical application, which can be considered as the replacement of the mechanical drill in dentistry. So, that is the typical application of the very short pulse laser. And pattern carving in the wooden structure without leaving the behind bar, that bar traces can also be observed, typical application of the short pulse laser. And of course, the short pulse laser also is very much applicable for the micro machining and the ablation process, and of course, it is suitable for the micro welding process. But as compared to that, long pulse laser, if we see the pulse duration is maybe nanosecond or the greater than that. So, that type of laser typical application, the medical application like skin treatment in macro welding processes. Of course, that long pulse laser can also be application in micro welding processes and cutting of the materials. These are the typical application for the long pulse laser. But if we see that right hand side this figure, here there is a comparison between the long pulse laser and femtosecond pulse laser, that means long pulse laser and short pulse laser. So, normally we see that long pulse laser, the size of the heat affected zone or molten size is little bit more as compared to the femtosecond pulse laser. So, if you see the femtosecond pulse laser is very precisely focused into a very small area, and there is may not be much sufficient time to transmission of energy around the surrounding material. So, whatever processing is required, it may be confined into the very small area. So, that is the advantages of using the femtosecond pulse laser. But point is that whether this femtosecond pulse laser is suitable for welding or not. So, it was investigated that pulse frequency may find pulse frequency having a role, whether the femtosecond laser can be used for laser ablation process or can be used for the welding purpose. Normally, if pulse frequency is very low, then it is suitable for the laser ablation materials, because frequency is low means within the small time gap there is a application of a continuous pulse energy. So, that energy actually ablated the material and without affecting the surrounding material. But in other way, if pulse frequency is very high, say in the range of megahertz, so in that range pulse frequency, this femtosecond laser is more suitable for the welding purpose, because the application of the pulse within the one cycle, the duration is very low in this case. Of course, in these two cases the average power may be the same, but there may be the change of the peak power, and the frequency of application of the laser pulses is maybe, if it is that span is very lapse is very high. So, in that case this situation is more suitable for the welding purposes. So, nowadays that ultra short pulse laser is more effectively used for the joining of the dissimilar metallic materials apart from the non-metals, because so far the ultra short pulse laser is used welding purposes, but more specific to the non-metallic material, maybe that in terms of the laser transmission welding. We will try to review that what are the in ultra short pulse laser domain, what type of materials we can use for welding purposes, and what type of laser we generally use for the welding purposes of metals or non-metals, or maybe dissimilar combination of the materials. So, it is very much significant that still there is a double development happens in welding processes using the ultra short pulse laser. Now, before doing that, we can discuss about the shape of the pulse. Of course, shape of the pulse is very much influential in case of the laser microwelding process. So, depending upon the type of material. So, there is several type of materials we try to weld using the laser, but we normally consider the shape of maybe square shape of the pulse and maybe within the pulse duration. But theoretically or logically, if we try to see that shape of the pulse having influence on the laser micro welding process or in general the welding processes. So, let us look into investigate what is the shape, how the shape of the pulse influences the laser welding processes. If we look into the first figure, here the shape of the pulse, rectangular shape of the pulse, but pulse duration is small in this case, but peak power is very high. So, when peak power is very high and pulse duration is small, so this type of pulse is more suitable for the keyhole mode laser welding, because within the short span of time there is a release of the huge amount of the laser energy. So, that is suitable to produce the high depth of penetration in specific in substrate material. Remember that area, actually that area of this rectangle represents the pulse energy. So, that pulse energy actually the power into the duration of the time. So, P into T. So, that actually represents the energy of the pulse, and physically represents this, the area of this is basically represents the pulse energy. But if we look into the other things, although in the second figure, so in this case if we see that there is a release of the energy, but the duration is little more as compared to the first case. So, of course, the same amount of the pulse energy second case, but peak power is less and duration of the pulse on time is more. So, this type of pulse is suitable in case of conduction mode welding process, because conduction mode welding process the peak temperature relatively less and there is a power density we control is relatively low, so that it may not vaporize the substrate material. So, that type of pulse is very much suitable for conduction mode welding processes. So, if we look into that, so shape of the pulse having in general having some influence on the laser material processing. First, if we see the peak power, if peak power is very high, probably that mainly controls the depth of penetration. If pulse energy per unit time, that actually controls the weld volume. So, weld volume is more sensitive to the pulse energy per unit time theoretically. And other way, if you want to keep the depth of penetration is very high, then probably the peak power is the more sensitive parameter in this case. And then frequency of the application of the laser energy, that actually creates the overlap or maybe overlapping spot in the sense. So, that frequency control that overlapping of the energy on the substrate material. And weld path, in general the path of the welding path, maybe since laser welder is confined to a very small area as compared to the arc welding processes. So, path may be more related to the distortion level of the sample. So, these are the parameters and how it is sensitive to the different conditions where we try to desire the whether high depth of penetration, or we need the large volume of the material, maybe conduction mode, or maybe if there is a need of the overlap, or if we want to control the distortion. For all these purposes, we should effectively use the different shape of the pulse, or maybe different laser parameters we can control, and we can link with this requirement according to the requirement. Now, point is that since if we see that two types, the more suitable in this case, that keyhole mode welding and conduction mode welding, we just simply changing the shape of the pulse. Similarly, if it is possible to create some complex shape of the pulse, then it is possible to weld difficult material, for example, very crack sensitive materials and high conductive materials. So, in that cases, in that type of materials which is very much difficult to weld, probably can be done if we properly design the shape of the pulse. So, that is why shaping of the pulse is advantageous, in the sense that when we try to weld the difficult materials, in that case if you correctly shape of the pulse, that is always will be able to produce some weld joint which is otherwise very difficult. For example, here the shape of the pulse in complex in nature, maybe combination of the some triangular shape or rectangular shape or some other shape. So, that shape having certain influence on the welding process. So, that will try to understand what are the shape of the pulse and what type of materials we can weld in this case. Let us look into this part. That first thing is the crack sensitive materials. If you see the design of the pulse in case of the crack sensitive materials, first is that upslope. At the start there is a upslope, that means gradually increment of the power beginning. So, this type of shape of the pulse actually prevent the thermal shock, that means with respect to the suddenly application of the pulse at time t equal to 0. Next, finally, that down slope at the end, that also controls the heating process. So, if it is possible to control the heating and the cooling process, so then it is possible to develop the welding process depending upon the shape of the pulse to weld crack sensitive material. So, these are the typical shape of the pulse in case of crack sensitive materials. But if we look into that other type of welding process, when there is a large tolerance is required. So, in that type of welding processes, we can start low peak power, but there is no gradual increment of the power, maybe power amount of the peak power in this case is very small. So, and if we keep it over a sufficient time, that actually melt first material, and then afterwards it melt the second material. Now, at the finally there is a gradual decrement of the pulse. So, that actually helps to stable the melt material and cool down to the weld joint, cool down to the ambient temperature. So, this type of shape of the pulse is basically helps when there is a large tolerance is required during the welding process. Now, if you look into the other type of the pulse shape, it is a high reflective material. So, high reflective material is really very difficult to weld using the conventional welding processes, but in using the laser welding processes, it is possible to weld high reflective materials. So, in that case, a good design of the pulse, shape of the pulse is advantageous for this case. So, if you see the shape of the pulse, here we can see that high peak power. So, high peak power is facilitated to start the melting point, because this high reflective material, they may be reflected the most of the laser energy. So, in that case, initially we can start with a very high amount of the power to start the or to initiate the melting process. Then once the molten material forms, then only there is a absorption of the laser power is actually increases after formation of the molten pool. And finally, reduced power and rapidly, but not gradually. That actually helps to the welding of the high reflective material. So, in this case, first very high power, then gradually reducing, but we can do that reduce power, we can reduce the power rapidly, and then gradually we can reduce the magnitude of the laser power. So, this type of shape of the pulse is very much suitable in case of the high reflective material. So, that means there is a role of the shape of the pulse in case of the welding of the different types of material. When there is a difficulty, and possibly it is useful when there is a difficulty in welding for the different types of material. Now, what may be the pulse parameters normally we consider, or sorry, process parameters we consider in case of ultra short pulse laser welding process, and in very specific to laser transmission welding process. So, here if you see that pulse energy, we know that pulse energy delivered in a single pulse, that represents the pulse energy, and power density, that number of laser photons impinging on the material, or in mathematically we can measure the power density, that simply application of the power divided by the cross sectional area over which it falls upon. Then pulse duration, the length of the pulse time that the laser pulse is on, and then peak power is the maximum power over which the it is focused on a specific object, and then pulse frequency, then it is normally in case of welding process normally it ranges from kilohertz to megahertz, and spot diameter, that diameter over which the laser is focused, that is the representation of the spot diameter. And the in case of relaxation welding laser transmission welding process, laser relaxation time is important when we use the ultra short pulse laser. So, in that case the relaxation time is basically defined that there is a lag to development of the heat flux or development of the temperature gradient within the domain. So, that lag time is very much important when there is a interaction of the substrate material with the ultra short pulse laser. So, we will try to explain that a typical shape of the pulse. If we see that it is a pulse shape over the time, and this is the power. So, normally we start with this is the over the time, this area actually represents the pulse energy. So, and this time span actually represents the pulse on time, and this total time is basically represents the cycle time. So, that cycle time is if frequency laser pulse application frequency is f, then cycle time is basically 1 by f. That means, this is the cycle time. So, over the cycle time, some part of the time is we apply the pulse, and remaining time there is a off time. So, there is no application of the pulse energy. So, these are the typical pulse and we generally use in case of laser welding process, but the shape we are assuming the rectangular, but shape can be different. But sometimes we use the average power also, but average power is maybe in between the peak power and the base power. So, for example, this is the average power, this average power is simply representation the some constant power over the duration of the welding process. So, it actually reduce the effect of the, or maybe eliminate the effect of the pulse on off in that mode that we generally use in case of the laser welding processes. So, sometimes we generally most of the cases we do the analysis of the process based on the average power, and sometimes we analyze the process based on the that peak power or maybe duration of the pulse. It is depending upon the different types of welding process, the analysis method can be different, whether we should consider the, if we consider the average power, it is very much equivalent to the continuous mode of laser welding process. So, it basically eliminates the effect of the pulsation, but if you want to do the actual analysis of the laser welding process based on the pulse, then we need to consider the pulse characteristic in terms of the peak power, pulse duration, pulse uptime, cycle time, that means in terms of the frequency, that all parameters are significant to analyze the pulse laser welding process. Now, we will further analyze the shaping of the pulse in micro welding process, and here what we have tried to do some simulation. So, that actually give the actual idea or maybe some feedback based on the simulation, we can find out the difference of the in terms of the output parameter when there is a change of the shape of the pulse. Let us see that, consider the material borosilicate glass, and the laser welding process is the laser transmission welding. Fiber laser has been used, ultra short pulse laser, pulse duration is 406 femtosecond pulse width, and pulse energy is 0.5 microjoule, and that pulse repetition rate or maybe frequency, that is 1 megahertz, and laser scanning speed the 1 to 10 millimeter per second. And in this case, two different shape of the pulse has been considered, one is a rectangular pulse, another is the triangular pulse, but in these two cases pulse energy are same, but geometric shape of the pulse are different. So, when you try to consider the effect of the pulse shape, we can see that we need to consider the other parameters. For example, the thermal wave speed of glass we estimated at 0.9 meter per second. So, with respect to that, the relaxation time for glass is 3.7 into 10 to the power minus 7 second. So, this relaxation time is little bit more as compared to the metallic material. For example, gold, that the relaxation time in case of gold is around 10 to the power in around 10 to the power minus 12, that means in picosecond level. Now, when we consider these things, that relaxation time, this is actually comparable as compared to the pulse width. So, this relaxation time is more as compared to the pulse on time, that means 406 femtosecond, which is comparable with respect to the 3.7 into 10 to the minus 7, that is the relaxation time. So, when the relaxation time is less, relaxation time is more as compared to the pulse duration, then it is better option to analyze this phenomena using the non-Fourier effect of the heat transfer mechanism. So, and this mechanism, because in this mechanism is based on that there exists some non-equilibrium state with the application of the femtosecond level pulse on the substrate material. So, using these two shape of the pulse, we will try to see that there is a time temperature history for this femtosecond pulse or maybe 0.406 picosecond pulse length, and using the ultrashort laser, and here we can see for a single pulse there is a little difference as that time temperature history within the substrate material. So, the peak temperature is high in case of triangular pulse shape as compared to the rectangular shape of the pulse. At the same time, peak temperature is actually far away from the end of the first pulse due to the presence of the thermal inertia. Actually, in case of when you try to analyze the effect of the heat transfer in case of normal or maybe large pulse duration case. So, in that case we assume the Fourier heat conduction. So, there with the application of the pulse energy within the surface, instantaneously there may be some development of the temperature. So, there is no lag or no gap between the application of the flux and the development of the temperature within the body. That is the basic assumption in case of Fourier heat conduction. But when you try to use the ultra short pulse laser, there may be some gap with the application of the heat flux and there is a development of the temperature within the body. That gap is characterized by the relaxation time for the specific material. So, that is why, but here if you see that there is a gap to reach the peak temperature and at the end of the pulse, and even to reach the peak temperature there is a little bit gap. So, this gap actually happens due to the thermal inertia effect within the body, and that is because of the there is interaction of the femtosecond pulse with the substrate material. Another observation is that there is a time lag due to the thermal relaxation in the hyperbolic nature of the non-polar heat conduction that we have considered in this case, and of course, temperature history differs with respect to the triangular and the rectangular pulse. Here is the typical simulation of the rectangular pulse shape at the scanning velocity of 1 millimeter per second, and the laser beam, because this is a laser transmission welding. So, laser beam is focused 50 micrometer from the top surface, then we can create this kind of weld profile, and of course, this analysis has been performed using the non-Fourier heat conduction model. So, heat is concentrated is very narrow zone, that is obvious from the simulation results, and the thermal conductivity of glass is actually less as compared to the metal. So, that actually leads to the development of the temperature over a narrow zone, that is also one reason for that. And then we did some simulation at the two different cases. One case is the scanning speed, that means laser moving speed is 1 millimeter per second, but in that case we consider the rectangular shape of the pulse. In another case, the scanning speed is 10 millimeter per second, but in this case the triangular shape of the pulse has been used. Now, you can see there is a huge difference in the time temperature profile at the two different shape of the pulse, but triangular pulse probably producing the more steep temperature gradient as compared to the rectangular pulse. This is one case, but due to there is a difference from the contraction stress acted inside the molten pool, and there is a with respect to the bottom surface. So, probably at the bottom surface there is a narrow part, and that actually creates some difference in the stress distribution on the molten pool and the bottom surface when the metal becomes solidifies. So, that stress concentration can lead to the crack generation specifically at the bottom side of the plate. So, in this case, if we try to avoid the crack formation, probably the rectangular shape of the pulse is more suitable, because the rectangular pulse is produce the least temperature gradient as compared to the triangular shape of the pulse. So, purpose of this analysis is to find out that since shape of the pulse actually influence the temperature distribution within the body, and that temperature distribution is also responsible to create whether any distortion or residual stress, at the same time whether there may be the formation of the crack, that actually can also be linked with the distribution of the temperature. So, distribution of the temperature is also influenced by the shape of the pulse. So, when you try to do some welding process in very smaller scale, specifically micro welding scale, in that case the shape of the pulse probably is very significant, very important. It may not be much important when you try to do the welding in case of the macro scale. Maybe in normal scale welding process, the shape of the pulse having little influence or may not have any influence at all, but in micro welding process or smaller scale welding process or even nano welding processes also, the shape of the pulse probably significant. Now, some simulation for the laser transmission welding material polypropylene we have used, and the other material properties are also defined. So, in this case the similar type of materials can be joined and the two sets, and considering the contact resistance between the two surfaces, and we can see the temperature distribution between the two surfaces in the laser transmission welding mode. And this figure also represents the comparison between the actual experimental and the some simulation profile. So, in this case that we can observe that in laser transmission welding, in case of even there are similar material, but maybe in the one both material are transparent, but at the interface if we use some absorbing material, that actually influence the temperature distribution of these two substrate material, and we can get this type of temperature distribution in case of the laser transmission welding. So, further analysis on the laser micro welding, but in this case the ultra short pulse laser heating process using the dual phase lag effect. If we see that since there is a phase lag, now if we see the figures, actually if we observe the figures, that from the first figure to the last figure, that peak temperature achieved is somewhere in between, maybe in figure E the peak temperature is achieved, but in this case if we look into the depth, the depth of penetration is low as compared to this last one. Of course, in the last figure there is a it is not as the peak temperature is low as compared to the figure E, but depth of penetration is more as compared to the figure E. That means, this simulation is signifies that with the application of the flux on the surface, there is a movement of the development of the temperature distribution that actually define the penetration. There is a some relaxation exists. That means, with the application of the heat flux, it is not instantaneously developing the temperature distribution with the certain depth. So, some time lag is required, some time lag is obvious, some time lag exists, and that is obvious from this all these simulated results. So, of course, this simulation has been performed using the effect of the dual phase lag over the 100 nanometer thick gold plate, and in this case 100 femtosecond pulse width has been used, where the peak power is very high, 2.66 kilowatt, and the pulse repetition rate or maybe frequency is 76 megahertz. So, with these conditions we can find out that there is a clear effect of the relaxation time in case of ultra short pulse laser heating process. So, this some other some results, that is we try to analyze the effect of the ultra short pulse or phase lag effect. So, here if you see the first figure, there is a typically shifting of the peak power, which is not obvious in when there is a pulse length is very high, maybe in the nanosecond or microsecond or millisecond level, there may not be the shifting of the peak power, and this shifting of the peak power only because of the lagging effect. So, similarly, pulse width effect having the, if you increase the pulse width, then there is a increment of the peak power at the different, if you increment the pulse width. So, peak temperature actually increases. In other cases, if we see that there is the effect of the relaxation time, since the relaxation time is very difficult to measure accurately, and of course, it also depends on the temperature, then there may be the, if we do the variation of the relaxation time, there is a maybe change of the peak temperature also, and both the figure also shows that peak temperature actually reduces with respect to the higher relaxation time. Here also peak temperature reduces in the with the higher relaxation time, but both these cases the nature of the increment of maybe nonlinear behavior generally observed in the with respect to the relaxation time with the variation of the peak temperature. So, after looking into that ultra short pulse laser welding mode, probably we can see the application of the laser microjoining processes. So far, that in practical use of the microjoining process in case of metals, from this table it is very much obvious that what are the different types of laser is used for the microjoining applications or using as laser. So, first pulse enduac laser, continuous wave fiber laser, pulse enduac laser, and direct laser and pulse fiber laser. These are the typical lasers so far practically applied in case of the microjoining processes and specific to joining the metallic materials. So, if you see the from the tabulated form that here the mean power is around minimum mean power is around 40-50 watt, but maximum is I think from this table is around 300 watt. Pulse energy varies. So, one cases it is 1 joule, another cases maybe 17 joule. Pulse length also varies 0.1 to 20 millisecond, other cases 2 to 4 millisecond or maybe 4 millisecond. So, in this case that means if you observe for the joining of the metals using the using the pulse laser welding process, we here that from the pulse length we can find the most of the cases we use the millisecond pulse for the microjoining processes specific to the metallic materials. So, here if you see the other power density reaches to as the maximum of 100 into 10 to the power 6 watt per centimeter square, probably it is on the around to the formation of the keyhole, and that comes from the continuous wave fiber laser. And normally bead on plate welding, lap joining, butt joining this type of welding joint has been performed using the different types of lasers and on different materials, stainless steel, aluminum, copper and titanium. Mainly this type of materials is applied in the pulse laser in the microjoining form, where the thickness, actually minimum thickness is found out from the literature that it is a 50 micrometer and minimum, so maximum it goes to 2000 micrometer. And weld dimension, if we see, the W means here width and D means the depth. So, here if you see that width and depth is around 65 micrometer to 300, 200 and 150, that might in that level the weld dimension can be produced. And this is a typical observation from the literature that for metallic materials the 3 or 4 types of laser can be used and for the micro welding applications and different types of materials. Now, if we look into the other non-metals for in the form of the laser micro welding processes, here if we see that pulse duration, normally we use the in femtosecond level and 350 femtosecond level, 947 and even 4 to 6 femtosecond level pulse can be used for the processing of the non-metals, and probably in this case only the in mode of the laser transmission welding. So, here the spot diameter is focused only on 4 micrometer. So, how precisely need to control on the using the ultra short pulse laser or maybe femtosecond pulse laser. Speed is around 0.1 to 0.2 or maximum 2 millimeter per second, and we use the different types of materials, specific all are non-materials, glass, silicon, all different types of material, similar combination of the dissimilar combination metals, and thickness in terms of micrometer can be produced around 50 micrometers. So, mostly the non-metallic materials is processed in the micro scale application using the femtosecond pulse laser and in the mode of the laser transmission welding. Now, dissimilar material combination can also be welded in the micro welding applications. Here we observe that typically continuous wave diode laser, fiber laser normally used. Average power output is around 2.2 watt to minimum 1 watt, and spot diameter maybe 300 micrometer, different speeds, but different types of material we observe that application of the laser in case of dissimilar combination of the material. So, polyamide and titanium, this joining of the two materials, two different types of materials, glass and polyamide, that combination, and polyamide and titanium, already we have seen that also polyamide and titanium with that combination of the materials for the dissimilar joint configuration, we found out the application in the micro scale. So, these are the practical application of the laser micro welding processes observed in the literature and so far have used also. Now, we shift to the plasma micro welding processes or maybe using a micro plasma arc welding machine. So, plasma micro welding process, the principle is little bit different from the laser. Here if you see the plasma micro welding processes, the only we have already idea that the plasma welding processes, but it is a same machine can be used, but it should be capable to control for micro welding application less than 15 ampere current can be modulated using the plasma micro welding process. So, principle of operation it in terms of the non-transfer arc or transfer arc process. So, non-transfer arcs means the plasma gas should be supplied, that gas with the electrode that can create the arc, but there is a need of another shielding gas in plasma welding process. If you see the shielding gas and plasma gas, two different gas is required for the creation of the arc and the shielding of the molten material. And you see, but we see the non-transfer arc in the normal process and transfer arc maybe when there is a if you want to produce a layer of the surface on the workpiece material, in that case maybe you can use the fine powder along with the arc. So, that fine powder can be coaxially projected along with the arc on the surface, then it creates a small layer of the surface. So, that type of arc is considered as the transfer arc process. For probably micro welding process, we generally use the non-transfer arc welding processes, but if you see for micro welding application using the plasma arc welding process, the current should be less than 15 ampere as compared to the other two modes, melt-in mode and the keyhole mode, or the cases the level of the current will be different in this case. Practically all types of material can be processed using the plasma arc welding process. Now, what are the different equipments for the microplasma arc welding process? So, definitely first is the power supply, DC power source, or the open circuit voltage is around 70 volts or above. A plasma torch. So, torch either it can be transfer arc type or non transfer arc type, and torch most of the cases found out the water cooled to increase the life of the nozzle and the electrode. And high frequency generator can also be used for the arc ignition, and maybe a self starter kind of things. Arc starting system is normally found out in the any microplasma arc welding machines, and the electrode is a tungsten electrode is used for the microplasma welding along with the copper nozzle. And sealing gas, we use the two inert gas or gas mixers can be employed at the sealing purpose. One, another is the for the generation of the plasma arc. So, maybe same type of gas can be used for the generation of the plasma arc as well as the sealing purpose, but two inert gas is used, sealing purpose can be used if we need some extra arrangement of the gas supply specific to joining of the titanium alloy, because titanium alloy the extra sealing gas of the required to protect the material from the oxidation. So, this is specifically required for the titanium, but it may not be required for the other welding processes. So, what are the process parameters specifically in microplasma arc welding process? One is that at least two separate and possibly three flow of the gases are used in the plasma gas shielding gas that we have already discussed. Gas flow rate is around 4 to 6 liter per minute. The current type and polarity, probably we use the DCEN, direct current electrode negative, in that form we use, so that in that form the maximum heat is generated on the workpiece and the certain percentage of heat is generated on the electrode material. So, that is why DCEN polarity can be used, normally used, but in very specific, for example, aluminum and magnesium or their alloy can be processed using the plasma microwelding process, but current mode should be AC, so that during as application of the current some 50% heat is generated on the workpiece and 50% heat is generated on the electrode surface. So, that actually in one cycle. So, during the one cycle the amount of the heat is generated on the one that actually acts as a cleaning action of the oxides layer in very specific to aluminum. Welding current is around, frequency is 20 kilohertz can be used. Welding speed depending upon the material, because normally when there is a increment of the welding speed, there is a less deposition of the heat to the substrate metal. So, it is some relation between the welding speed and the heat input to the substrate material. So, normally we use the, for example, 0.5 millimeter thick of the titanium or steel, maybe 1 to 5 millimeter per second, within that range we can use the welding pitch in case of microplasma arc welding process. So, electrode diameter can be used as, normally we use the 1 millimeter, or definitely it depends upon the application, or maybe sheet thickness or at what is the amount of the penetration is required. Based on that, electrode diameter can be chosen, but normally we use the 1 millimeter diameter of the electrode. So, like laser welding process, plasma current can also be made in the pulse form, but the shape of the pulse is using the square shape of the pulse, where the most of the welding cases we use, but it is very difficult to control of the shape of the pulse like laser welding process in case of the plasma welding process. So, it's a not much variation of the shape of the pulse, specifically not variation of the shape of the pulse is possible in case of the microplasma arc welding process. So, peak power pulse width, all like the laser welding process, we can use the normally pulse width in terms of millisecond, but we can choose the pulse width, but at the same time peak power or maybe peak current or base current we can use it, and accordingly we can estimate the what is the peak power in case of, because power is in case of plasma arc welding is equivalent to the volt into ampere. So, average power can also be estimated like laser welding processes, also similarly pulse repetition rate that actually represents in terms of the hertz. But in this case plasma microwelding processes, probably two things, one is the peak current and the base current. Base current may not be 0, some certain current value we should use as compared to the peak current. So, purpose of the using the pulsation even for the plasma microwelding processes, that actually helps to join specific to the very thin sheet application. Basically, the ramping of the power in this case helps to join even much smaller thickness of the material. That is the purpose of the pulsation even in case of plasma microwelding process. Now, we shift to that point, that electron beam microwelding process. So, of course, we already learned that probably the electron beam or laser beam can be used when there is a requirement of the high depth of penetration, but in that case the huge power is normally electron beam produces the huge power, and that power is concentrated over a narrow zone, and that is responsible to create some high depth of penetration. But if we use some other way the electron beam, and it is in case of microwelding processes, then it is possible to produce even for low depth of penetration. So, what in most of the cases of course, is almost welds are conducted almost in the vacuum. So, in that cases the joint properties is very much attractive or maybe very good quality as compared to the laser or some other welding processes. This is the first priority that in case of electron beam welding process. Second thing is that power beam normally 100 watt to 5 kilowatt is available in the market for conventional welding process, but that range of the power is not suitable for the micro scale application. But if we compare as a laser, conventional laser, that sometimes very low power laser also suitable in case of the microwelding process if we follow the proper pulsation of the laser power, but that is not the case of the electron beam welding process. So, in that case researchers also found out that simple modification of the scanning electron microscope optics, electron microscope, and specific in optics, it is possible to produce that for micro welding applications. So, this technology has been developed by the GIS company, but it is having the maximum power of 6 watt. Now, look into that, in which principle the same works. Basically, the purpose of the scanning electron microscope, of course, here the source is the electron, but try to produce the lowest possible energy input, but with the high resolution. That is the basic principle of the scanning electron microscope. But if you see the scanning electron microscope basic structure or their optical structure is like that, electron source is there, and then condenser lens and aperture, objective lens, and then we observe the observing specimen is there. So, that is the typical optics in case of the scanning electron microscope. But here if you see that multiple apertures are used, but what is the purpose of apertures? This is basically apertures is used for the screening of the off axis electrons, and here two condenser lens are used for the reduction of the excess electrons, and finally creates the low power beam with the extremely small focused spot on the sample surface. So, this is the basic principle of the scanning electron microscope. But if you look into that modification of the scanning electron microscope in other way, simply in the if you try to make in the micro welding mode the removal of the apertures and the one condenser lens. So, out of the two condenser lens probably or more, if it is possible to remove all the condenser lens and apertures, that actually makes suitable for the micro welding application. So, the micro welding application, the optics is like this. Here if you see the apertures actually reduces the effective beam power. So, this removal of the apertures probably effective beam power can be increased. Second modification is that removal of the condenser lens, probably not the excess electrons are not removed in this case by removing the condenser lens. So, in this mode the same electron beam source can be used as a micro welding application. So, but modification is reversible in the sense that it can be used either scanning electron microscope or micro welding application. So, that type of instrument is available in the market. So, what are the typical application of the electron beam welding? We found out that joining of the thermo elements basically made of nickel chromium or nickel wire typical dimension, and basically that can be used for the temperature measurement, these things, and other application of these things. Heat conduct, the materials with the favorable heat conductive properties that can be processed using the microbeam welding process. So, such as copper, aluminum, sometimes micro source of the electron beam can be used the soldering application as well, but this can be used more is the welding of the liga. Nearly liga is the one type of material that is almost pure nickel, that joining gear to the tool steels gauge pin. So, in that typical application the electron beam welding can be used. Now, if we look into the resistance micro welding, the heat is generated by the electrical resistance of substance to the passage of the electric current. So, in this case the same principle that non conventional resistance welding principle, it works on the conventional resistance welding processes, but that we know that mainly the heat generation is the due to the resistance exist with the passage of the current. So, resistance exists in between several contact surface as well as the within the bulk metal itself. So, if we consider all the resistance include, and then heat is generated by using this formula H equal to I square R T. R is the applied current, T is the time duration, and R is the resistance, but R resistance should be considered all the resistance of the contacting surface of the circuit. Here we see the contacting surface is this tongue, electrode and workpiece material tongue, and between these two, between all these elements we need to calculate the R resistance, and that is responsible. But we will try to see how this resistance micro welding is different from the conventional micro welding is different from the conventional welding process. If you see, the electrode pressure in this case is much lower in the micro welding processes, definitely as compared to the conventional welding processes. So, because much lower electrode pressure basically results in the high contact resistance, and when there is a high contact resistance also reduces the welding current, and of course, the difficulty is that it promotes the electrode sticking. And there it is observed that maximum nugget diameter in case of resistance micro welding process is around 33% of the electrode diameter, but chances of the electrode sticking is more in case of the micro welding applications, because specifically in micro welding applications the electrode size is small. So, there is no scope to cool using the water cooling process of the electrode, and that normally in case of conventional resistance welding process water cooled is followed because the size of the electrode itself. So, because of the size restriction there is a chances of the sticking of the electrode is the main obstacles in case of resistance micro welding process. But in terms of application, the most of the non-ferrous metals and alloys are used or processed using the resistance micro welding process, but for regular micro welding processes we mostly steels are processed, and but in case of micro welding mostly we use the coated steel with silver, gold and nickel etc. But for regular, or that means conventional micro welding processes, the usually processed or usually welded using the uncoated or coated with the zinc. That type of metals is suitable in case of or mainly applied in case of conventional welding processes. But after the welding processes of the different welding process of the metallic materials, but if we focus on the micro welding of the plastics, here the practical importance is the micro welding of plastics is specific to medical devices and the electronics devices, where complexity in structure exists. Specifically in that case the micro welding is more suitable, where the most complex structure is processed can be processed using the micro welding process, using the different micro welding processes of plastics material. So, even it is used manufacture of polymer component, even very few micron size is possible using this methodology. Joining of the 100 micrometer is wide is open sometimes required, and sometimes the sealing of the metal is required in case of micro components. So, that sealing of the materials using the plastic component is processed by the micro welding of the plastics. But of course, there is alternate for the adhesive bonding or adhesive joining processes, but in the advantage of the adhesive process is the no heating is required, but sometimes the curing time may be significant. So, alternate is the welding process. Of course, in this case the small heat affected zone has been created, but definitely it affects the coating or the surrounding equipment in a very in a specific device when there is a compacted of the several components are there. So, in that case, if these are the two different advantages or disadvantages of the microwelding the plastic. So, there is a separate module for the discussion of the micro welding of the plastics material. So, I am not repeating the same thing here again, but in the trying to focus on the different types of processes that can be used in the micro welding applications. But main thing is that during the micro welding applications in specific to plastic material, here you see the heat generations, it basically comes from the mechanical motion. So, based on that it can categorize, or there are several techniques exist. One is the spin welding, vibration welding, ultrasonic welding and friction stir welding. All these cases the heat is generated by the mechanical motion of the material. So, second is that from external heat source, hot plate welding, hot bar welding, the impulse welding, hot gas welding, extrusion welding, these are the typical welding processes, and where the heat source is externally applied, and of course electromagnetism that also is the drives the micro welding processes of plastics. Basically the typical welding processes includes that implant welding, induction welding, dielectric welding, microwave welding, infrared welding, and of course the laser welding. So, all this comes under the categorization of the electromagnetism. So, the brief discussion of the different welding techniques for plastic, there is a separate module. We will try to discuss that on that separate module. So, thank you for your kind attention.